Most electricity in the United States is produced by using fossil fuel. In this presentation, we'll look at the process by which fossil fuel is turned into electrical energy. Most electricity is produced at power plants like the one shown here, and that electricity is put onto the electric grid. Most power plants consume fossil fuels such as coal and natural gas. Some power plants also consume nuclear fuel. This slide shows how electricity is produced in a coal-burning power plant. Coal is burnt. The heat from the coal heats water until it becomes steam. The steam then runs against the turbine blades, turning the turbine, that's the red thing in the middle, turns the turbine shaft. The turning shaft then turns the shaft inside of the electric generator. That motion inside the electric generator produces electricity. Electricity travels along the transmission system, the grid wires, until it gets to the end user, and in this case the end user is making toast. To complete the cycle within the power plant, the steam then has to be condensed, has to be cooled off, and you need cooling water for that, so you need a cooling tower or some other source of cooling liquid, cooling water. The steam has to be condensed so it can be reintroduced and to be heated up again. So that's the complete thermodynamic cycle, the water turning to steam, the steam turning back to water, and running this whole process. In the US, as in the rest of the world, coal is the largest fuel source for the production of electricity. In the US, about 39% of electricity is generated by burning coal. Another 27% comes from natural gas. About 19% comes from nuclear and renewables, that is wind and solar and hydroelectric, produces about 13%. A very small fraction comes from the burning of oil. Oil is mostly used for transportation. The share of electricity generation by coal has been decreasing. It was just a few years ago that roughly half of the electricity in the United States was generated by burning coal, but that fraction is steadily dropping. We're going to take a quick tour to see how electricity, the whole cycle of electricity generation in a typical coal burning power plant. In this case, we're going to look at the coal burning power plant, the generating station in Bridgeport Harbor. To begin with, you have to have coal. The coal that we use in the East Coast now mostly comes not from the East Coast, but most of it actually is coming from the West. A lot of coal is being mined in Wyoming, and because that coal can be mined fairly cheaply, it's also relatively clean coal. It's low sulfur coal. Here we see not a very clean or pretty operation. This is a surface mining operation or strip mining operation, and here there's a lot of impact on the soil, obviously on the environment, and this land will have to be reclaimed, brought back to something like it was before the strip mining operation began. The coal then that's mined in another state, Wyoming for example, that's going to be burned in Connecticut has to be shipped here, normally shipped by train. It's very bulky stuff, but once coal gets to the site where it's going to be consumed, it is piled up and stored on site. There's a big pile of coal. That coal will then be used as it's needed to to be burned in the coal burning furnace. Here we see a coal burning boiler, a furnace. The coal that's burned in these furnaces are ground up so it's powdered, and it can be oxidized most efficiently, and is then used to produce the heat that will be used to produce steam to turn the turbine blades, to turn the turbine shaft, to turn the electric generator. Here we see the inside of a steam turbine when it's not operating, and we can see that on the left-hand side, you can see that there are the blades that the steam hits and causes that steam turbine to turn. Here's the electric generator. The electric generator is the device that the steam turbine shaft operates the electric generator, producing electricity. So this is really where the electricity is produced. Here, looking inside the steam generator, the concept here, if you've had physics at some point in your life, you know that the concept is you're turning a wire in a magnetic field. See, on the right we see a schematic of that. So we're turning this loop of wire in a magnetic field, and that produces, by electromagnetic induction, produces electricity. And so what the steam turbine shaft is doing is actually turning this loop of wire inside the magnetic field inside of the generators. Once the electricity is produced inside the generator, then that electricity is put onto electric wires. That's the plant output. The plant takes all this coal in and produces electricity. The electricity leaves the plant on these high voltage wires. So that's the plant output. This plant output, the electrical output, of course, is AC, or alternating current. It's not like a battery voltage. It's like the voltage that you would get if you plugged into a wall socket. So it's alternating current. The advantage of alternating current is that you can use a transformer, like we see on the right, to up the voltage, to go to very high voltage, tens of kilovolts, to go to very high voltage, to transmit the electric power efficiently. The United States is divided up into a number of different grids. So if you look here on the East Coast, where Eastern is, there's a New England grid. You can see there's also Southern grids. There's a Western grid. There's a whole bunch of grids that are tied together and they share electricity. You notice that there's no connection between the Western grid and the Eastern grid, and that Texas has its own kind of grid, so it's kind of separated from everybody else. So those grids tie together, they share electricity, and one of the things, of course, in the past, when the grid was less reliable, if something went wrong in the grids that we were connected to, then the whole grid could go down, and that certainly happened in power failures of the past. The grid includes not only the power producers, but also the transmission and distribution. So from the power plant, that electricity has to get out, has to be transmitted to an area where it's going to be used, and once it gets to that area, it has to be distributed. The transmission is done with high voltage wires. So we look at a high voltage array like this. I'm sure you've seen these in the countryside. The advantage of this is high voltage means low current. Low current means low losses. So this is more efficient. You're losing less electricity because you have high voltages. But some of the electricity, about 8% of the electricity that's generated at the power plant, is lost in the grid. That is, that some of that energy is just going to be lost in these wires. The wires heat up. If you've stood underneath higher voltage transmission lines, you can see and hear sparking, and you can hear some noise. So that some of that energy is being lost, and you can see that or hear it. Once that power gets close to you, the end user, gets close to, say, a residential area or a commercial area, there's a power substation which drops the voltage down and puts it on a voltage level that it can be distributed within a neighborhood or within a series of commercial establishments. In a residential neighborhood, the last step before it goes in the house is that array of things on the power pole. On the power pole, there is a transformer that steps the voltage down so it's appropriate for the house. so you don't have real high voltages, dangerous voltages inside the house. Then there are also wires that make sure that the electricity is a closed circuit and it's safe. Before the electricity can be used by you, when it enters, before it enters the house, it goes through a kilowatt-hour meter where the amount of electricity usage is recorded. Remember, we're recording the amount of energy, not the power, but the amount of energy we use in kilowatt hours. Once the electricity is inside the house, then a whole variety of end uses, including making toast, lights, maybe heat, lava lamps, all kinds of things inside the house where we use electricity. Okay, let's go back to the power plant. The power plant, a very important characteristic of the power plant is its capacity. So a big power plant might be able to produce 500 megawatts, 500 million watts of power at one time. So that would be its capacity. A small plant might produce 100 megawatts. A very big plant like a nuclear power plant might produce 1,000 megawatts. So that's its capacity. That's the most electricity it can produce. So you can imagine there's a power plant. On the side of it someplace, there's a little plate that says the capacity of this plant is 500 megawatts or 200 megawatts. So that's the maximum power that plant could produce. The other really important characteristic of a power plant, in addition to its capacity, is its efficiency. So an efficient plant might be 40 or 50% efficient. Most power plants are 33% efficient. And that means the efficiency is the electric power that's actually delivered to the consumer, divided by the thermal power that goes in. So if you say, I put so much fuel in, and that fuel inside the boiler with released energy, the efficiency tells you what fraction of that energy that is released becomes useful electric power. The higher the efficiency is better, because we have to burn less fuel and have less of an impact on the environment. Using fossil fuel to produce electricity involves three different kinds of impacts. One is the actual mining operation itself, to get the coal or get the natural gas out of the ground and bring it to the site. The second is when you actually burn the fossil fuel, then there are gases released up the chimney or the smokestack, and then these go into the environment. These include things like acid rain, or contribute to ozone or ozone pollution and smog, and also mercury pollution. So we'll look at this in great detail later in the course, but we know it's a problem. The third kind of impact we're already familiar with is that burning fossil fuel produces CO2. So if we look here in this table, the emission coefficient on the right for coal is very big. So if you had 1 million kilowatt hours, you would produce something like 982 metric tons of CO2, a lot. Natural gas is a lot less polluting. It produces less than half of the amount of CO2 that coal does. So it'd be better to burn natural gas than coal. And as people call that fuel switching from coal to natural gas. Then we see nuclear power and wind power or other renewables have virtually no emission. We're going to look then next at nuclear power, and then eventually at wind energy and other renewables.